Okay, so today we are going to start our first actual topic for the course. So far, we have been doing the basics of environmental fluid mechanics, or we have been revising some basic concepts. So today we are going to start plumes, buoyant plumes. And if you are not aware of this word plume, then let's try to first understand that what exactly it means. So you may have seen the images that are shown here on the screen. There are several examples I'm considering, and what you see here, these are called plumes, the top four images, not the bottom two. So the first one here is, you can call it smokestack plume. This one may be called a geothermal plume. This one is a volcanic plume, right? And this one is basically oil smoke plume. So these are different type of plumes. And what exactly is a plume? What is happening here? So in this case, there is a hot gas coming from a source, right? If you take this example, for instance, this white colored hot gas is coming from the plume stack, right? The smoke stack, and it is creating a sort of plume. Likewise, in case of geothermal plume, a black colored hot fluid is coming from a source. In actually it's in seawater, right? And that's creating a plume. And what exactly it means? So there is hot gas or hot fluid coming out, and it is moving upward. At the same time, it is also becoming broader. As you can see, the thickness of the plume is continuously increasing as we go up. Likewise, in this case, you can see how the diameter or the thickness is increasing. In all these cases, the same kind of behavior is observed. The thickness or the radius of the plume is continuously increases as we go up from the source, right? And in all these cases, the plumes are rising, they are going upward. That is because the hot plume is coming from a source. Okay, so we will discuss more details about the plumes, but let's quickly see a difference between plumes and a jet. So these two images that you see here, these are jets. Okay, in this particular case they are water jets, but there can be other form of jets as well. Okay, and what is the difference between these two? So as I said, plumes are driven because of temperature difference or density difference, which might be coming because of concentration difference as well, but primarily they develop because of a density difference between the source fluid and the ambient fluid, right? Whereas in case of jet, they may not necessarily have a density difference. They run or they develop because of momentum, because of velocity. So in this case, the fluid that might be coming from here, this particular fluid or this fluid, which are basically water, they have higher velocity, or they have velocity compared to the ambient. In that, velocity differential actually creates momentum flux, and that momentum actually drives the flow. Now in left hand case, you can see that this is water and this is also water. So basically there is no density difference between them, but there is a momentum difference. The injected fluid has higher momentum, higher velocity, and that's why it rises up. Okay, likewise in the case 2, now there is a density difference, but you will notice that this is water that is going up in air. So in fact, water is heavier than the air, but still is going up, right? And that is happening because it has momentum, it has higher velocity. Whereas in case of plume, initial momentum may not really be important or may not really be needed. Even if they don't come with a higher velocity or with any velocity, this will still rise. Why? Because there is a buoyancy force involved with it. Okay, because this is lighter density than the ambient, it actually rises up because of the buoyancy force. Okay, whereas in case 2, momentum actually, jets actually form because of inertia force, because of the velocity. Okay, so here are some more characteristics of plumes, and also in comparison with jets. So first of all, plumes are primarily vertical flows, okay, driven because of density difference, which is also generally known as buoyancy flux. So whenever there is a density difference, there is a buoyancy in the flow, there is a buoyancy difference, or there is a buoyant force, right, buoyancy force. And that is why flow is mostly in vertical direction, because buoyancy force acts in vertical direction, right? That's happening because of the gravity, or it works against gravity, and that's why it has to be in vertical direction. So plumes are primarily vertical flows, whereas jet, for instance, can also be horizontal. They don't really have to be vertical. And then plumes are usually generated from an isolated source, or single source, as we saw in these cases, right? We see multiple plumes from different cases, but they all coming from single source individually. Okay, and this particular point is important. Plumes may be both dense and light. Okay, so what we saw in previous slide, all these cases here, they are all light plumes. We have heavier ambient, lighter fluid coming into the ambient, and it's creating plume of lighter density. Okay, whereas if in the same ambient, if you inject denser fluid from the top, it will actually go down, and in downward direction it will create a plume. For instance, if uh, you have an injection point here where this rho is coming out and this is rho ambient, and this rho is greater than rho ambient, then it will create a plume which is going downward, and also in this case your radius of the plume will continuously increase as we go down. Okay, so that will be a dense plume when it goes down, but the behavior will be very similar as a light fluid, light plume. Okay, now when you compare plumes with a jet, in that case we saw that jets are driven due to momentum flux or initial velocity. So in case of jet, velocity is very important, momentum flux is important. It may not have any density difference with the ambient. Like in this case we saw both are water, so delta rho in this case may be 0, right? But there is initial velocity, and that's why jet is formed. So that is the major difference between a plume and a jet. Okay, and jet may also be horizontal, or it may be downward, it may be in very different directions, but uh, plumes are primarily in vertical direction because buoyancy force. Okay, and then in today's lecture we are going to consider plumes mostly turbulent in nature, and in fact it is mostly turbulent in nature, except if it is formed in porous media, and that is another sort of plume we are going to see later in the course. But in the beginning, for next few lectures, we are going to focus on turbulent plumes. Okay, and the examples that we just saw in the last slide, they are also all turbulent in nature. And because they are turbulent in nature, we have seen in the definition of Reynolds number, the viscous force are generally insignificant, or extremely small compared to the inertia force, right? And that is why, while modeling plumes in this clear medium, or turbulent plumes, we may neglect the viscous effects. Okay, we will only consider the inertia force, because viscous forces will be extremely small, and that will make our problem much easier to solve, and we will see how do we do that. Okay, and moving forward, we will start with plumes in unstratified medium. So what is an unstratified medium? So ambient density is constant. So unstratified medium is constant ambient density, right? This is something we have seen already. What does stratification mean? And we will start with unstratified medium, but later we will also consider plumes in stratified medium. Okay, So let's start with plume parameters for unstratified case. So how does plume form, and how do they grow? What all different parameters are important for our modeling or solving a plume problem, right? So here we will consider that this is rho ambient, rho A is rho ambient. So basically is the density of the air that is surrounding the plume, or in this particular is the atmospheric air, right? So density of the atmospheric air. Now there is the hot plume that is coming from here. So right, so here we see this hot plume. So it is hot, and that is why it has lighter density. It has density which is smaller than the ambient, or smaller than rho A. So let's call it rho naught, which is smaller than rho A. So rho naught is the source density, or density from where the plume is coming out, and here it is smaller than the ambient density. Okay, so and because now there is lighter density, it goes up. At the same time, there is, apart from the density difference, it might be coming with some volume flux. It must have some volume with which it is coming. So we will call that as q. So q is the, let's call it q naught. So that is source volume flux. Okay, so we see that there are two particular things because of which this plume is getting formed. One is the density, which is smaller than the ambient, and then there is a flux. So that gas which is coming out must be coming with some mass. It must have some mass or some volume, right? So we will call it source volume flux. And what are the units? Source volume flux must be meter cube per second. That is the volume of fluid passing per second of time. Okay, or getting released per second of time. And in the unit for the density should be kilogram per meter cube. This is the unit for the density, and that we know already. So now if you want to define few parameters considering density or volume flux, we will start with a particular parameter called reduced gravity, which actually signifies the effect of density difference. Okay, and this is written as g prime. Okay, so g prime is defined as delta rho divided by reference density multiplied with g. Okay, so delta rho is the density difference between the lighter fluid and denser fluid, which is divided by the reference density. And now when you multiply that with g, that gives you a thing called reduced gravity. So basically it's the effect of density difference and gravity together. Okay, and this signifies how much buoyancy force the hot fluid has for it to rise upward. Okay, so in this particular case, this is the general definition of reduced gravity, but for now we can define g prime naught, which will be delta rho, or in other words we can call it rho a minus rho naught divided by rho a into g, where rho a is the uh, reference density or ambient density in this case. Rho naught is the source density or plume density, right? And g is the gravity. Okay, so this is a parameter that's called reduced gravity, and this is very important in defining buoyancy driven flow. All right, and now we know there is this parameter, so we can define one more parameter, because there is one more parameter that is involved here, and that is the source volume flux. So what we will do, we will find a common parameter that can define the effects of density difference and the volume flux together. Okay, so that is the other parameter is called buoyancy flux, which is basically will be written as B naught, or that is usually written as B. Okay, so B buoyancy flux is given as Q times G prime. Okay, so volume flux times reduce gravity. Okay, and now because we are trying to define for the source condition, so we can write it as Q naught G prime naught, that will be, that will give us source buoyancy flux. Okay, so this is a parameter that we are going to use. So what exactly we are doing here? First, we define reduced gravity, which signifies the effects of density difference in combination with the gravity, right? So that is G prime naught. And now when we multiply that G prime naught with Q, that's the total flux that is coming out. The multiplication of them together give us a parameter called buoyancy flux. And now this buoyancy flux is the total, let's say, potential of the hot fluid that is coming out to form a plume and to rise. So the behavior of plume will now depend on B naught, which is a combined effect of both the volume flux and reduced gravity. Okay, and now let's look into the units of both G prime and buoyancy flux. So G prime, as we have seen, is given as Q delta rho by rho into G. So delta rho by rho have the same dimension, right? Delta rho by rho. So it basically has the dimension of, is simply of G, or okay, let me, okay, so what does this square bracket mean? We are trying to define the dimensions, right? So we know that this delta rho and rho must have the same dimensions, and that's why they cancel each other, and this effectively mean that G prime has the dimension of G, which basically is meter square per second. Okay, that is something we already know. All right, and now we can also define the same thing. So G prime and G prime naught will have the same dimension, so we can also write for G prime naught is basically the same as meter square per second. Okay, and in the same way we can define for B, which is Q times G prime. So Q has the dimension of meter cube per second, and this is meter square per second. Okay, so I think I'm already making a mistake. It has to be meter per second square. Right, this is a silly mistake. All right, and that is why this has to be square, and this becomes meter to the power 4 by centimeter cube. Okay, this is the dimension of B and also B naught. Okay, so these are two parameters we have defined, that is reduced gravity and buoyancy flux, and we are going to use them for our uh, calculation now. Okay, so now let's coming back to the plume, and we see what different sort of behavior we find in case of plume. So let's assume that there is this injection Q naught and G prime naught, right? And that is creating a plume as we saw in the previous slide. Okay, so we are assuming that rho ambient is constant, so that actually means that medium is unstratified, so rho is not changing with the height, so rho is not a function of z. Okay, and now what exactly happening here is there is an entrainment, a parameter called entrainment, as you can see here, is creating sort of eddies, turbulent eddies, and through that actually this the hot fluid actually engulfs ambient fluid and it mixes within itself, right? And that is why the diameter of the plume actually goes increases as we go up. Okay, so let me pull that picture here that I think will be easier to explain. Okay, so we are assuming that there is Q naught and G prime naught, effectively there is B naught, right? So what happens here is when plume is rising, this hot gas is rising, it's actually mixing a lot of ambient fluid in itself. So it has this turbulence, right, which turbulent eddies that actually engulfs or mixes ambient fluid in itself, and there is a lot of different kind of processes happening. So there is this shear mixing that we discussed, that's happening, there is maybe molecular diffusion happening, so everything happening together, right? And this overall process is called entrainment. This overall process of mixing between the plume and the ambient fluid is called entrainment. Okay, so basically this ambient fluid is getting entrained into the plume, and that is why this volume of the plume is actually rising as we go up. So we can see the diameter is increasing as we go up, as we go up from here, right? So that diameter is increasing, or indirectly the volume of the fluid is increasing, right? So there is a certain amount of volume coming out, that is Q naught, but as you go up, which is Q of Z, this Q of Z is actually greater than Q naught. So this Q of Z, there is greater than Q naught. Okay, so Q naught had certain volume per unit time, but as you go up because of mixing, there is extra fluid that has come into the plume, and that is why the total volume that is now rising up is greater than the injected volume, right? And at the same time, because there was density difference G prime naught, that was delta rho between the plume and the ambient in the beginning, now as it rises and there is entrainment of ambient fluid, it the plume actually gets diluted as it goes up slowly. There is dilution, there is less and less density in the plume, right? So let's call it rho p, which is a function of z, and we know that in the beginning there was this rho naught. So rho p, which is a function of z, is actually smaller than uh, no, in this case it has to be greater than rho naught. Why? Because there is more ambient fluid coming, it mixing, and that means the delta rho is decreasing, right? So here we had this delta rho in the beginning, let's call that delta rho naught, and here now there will be delta rho. So delta rho as a function of z will be smaller than delta rho naught, where delta rho as a function of z is rho a minus rho p, that is actually smaller than rho a minus rho naught, right? And because of that, your g prime as a function of z is actually smaller than g prime naught. And so that's what happening here. Because of mixing, your total density difference at different height with respect to the ambient fluid is decreasing as you go up. In the beginning, the density difference between the plume and the ambient was more, and as you rise up because of mixing, it gets diluted, so that delta rho is decreasing as we go up from the source. Okay, and that is why here we see that while q of z increases with z, where let's define this as z. Okay, g prime of z decreases with z. Okay, so volume increases but reduced gravity decreases. Okay, and in what actually happens is that characteristic of plumes in an unstratified medium, that this q times g prime, which we can define as buoyancy flux, is actually constant. Okay, we have seen that q increases and g prime decreases, right? Q increases, g prime decreases, and interestingly, both of them either increase or decrease in similar proportions, so that the multiplication of them remains constant. So when b remains constant, so b is simply is equal to b naught, which is constant at all elevation. So b is actually not a function of z. Okay, volume flux is increasing because of entrainment, density is decreasing, or density difference is decreasing, again because of dilution, but the both the things are happening together, that the total effect on buoyancy flux remains unchanged, right? So buoyancy flux remains constant at different elevations. It remains, it doesn't change with height. Okay.